Assalamualaikum and good day everyone. In this video, I'll be sharing on topic related to the serviceability of reinforced concrete. The subtopic will be learning are cracking, deflection and detailing of reinforced concrete beam. Cracks are induced in reinforced concrete element as a result of first, flexural tensile stress due to the bending under applied load. So you can refer to Picture 1 on the flexural cracking. 2. Diagonal tension stress due to the shear under applied load. You can refer to Figure 2 for the diagonal cracking. 3. Volume changes due to the shrinkage, creep, thermal and chemical effect. You can refer to Figure 3 for the volume changes cracking. And 4. Splitting along reinforced concrete due to the bond and anchorage failure. So you can refer to Figure 4 for the splitting cracking along the reinforcement. The main objective of crack control is to limit the width of individual crack. This is not just for the aesthetic reason, but most importantly is the durability and particularly for the corrosion protection of reinforcement. For control cracking, two alternative methods are described in Eurocode 2 section 7.3. First, we control the cracking without direct calculation, and second, we calculate the crack width. Initially, we cannot stop cracking to occur, but we as a designer can control or put a limit on the crack width. We should refer to Table 7.1, Eurocode 2, to know the recommendation value of crack width W max. It is basically depends on our exposure class. For structure class XO and XC1, the limit of crack width is 0.4 mm. As the structure class increase, the limit reduced to 0.3 mm. We also can control crack indirectly when we conduct the following checking. First is minimum reinforcement area, maximum spacing of reinforcement, and maximum bar size. The minimum area of reinforcement is to control thermal and shrinkage cracking within acceptable limit. The formula to calculate the AS minimum is 0.26 FCTM divided by FYK B times D. B is the breadth of our beam, D is the depth of our beam, FCTM is the tensile strength according to table 3.1. This formula should not less than 0.013 B times D. For the limit for AS maximum, we use the formula of 0.04 AC. AC is the cross-section area. If beam, it will be B times H. When we should calculate AS minimum and AS maximum is after we determine our area of steel reinforcement for beam. We must to make sure that our AS within the range of AS minimum and AS maximum. This is table 3.1, page 29, Eurocode 2. This table actually provides all the mechanical properties of concrete according to the strength of concrete, FCK. You can find the FCTM in fourth row from the table. So this first row, second, third and fourth. For example, if our strength FCK is 30 MPa, our FCTM is 2.9 MPa. When we already determine number of bar required for our beam, we should arrange the bar. The spacing between bars should permit concrete flows around reinforcement during construction and to ensure that the concrete can be compacted satisfactorily for the development of adequate bond. The clear distance between bars should not be less than maximum of bar size, aggregate size plus 5 mm or 20 mm specified in Eurocode 2. We use table 7.2 and 7.3 for crack control. In table 7.2, we check our maximum bar diameter, and 7.3 is for maximum bar spacing. In these two tables, we required steel stress. We use this formula to calculate our steel stress. For maximum bar diameter, we have crack width of 0.4, 0.3 and 0.2. Once we get our steel stress and crack width, we can determine our bar size. Similarly, for maximum bar spacing, all of these values are the value of spacing between bars. Now we move on to the deflection. Excessive deflection leads to sagging of floor, crushing partition, buckling, lifting doors, poor drainage, and so on. For controlled deflection for beam, two alternative methods are described in Eurocode 2, Clause 7.4. First, we limit span to depth ratio, and 2, calculation of actual deflection. This is the two deflection limit for our beam. Final deflection of beam subjected to quasi-permanent load should not exceed span divided by 250. For the deflection which take place after application of finishes or fixing of partition, it should not exceed span divided by 500 to avoid damage to fixtures and fittings. To control deflection of maximum span divided by 250, easy to provide two formula for basic span effective depth ratio L over D. These two formula depends on the value of rho and rho O. What is rho O? So rho O is the reinforcement ratio, reference reinforcement ratio calculated by 10 to the power of negative 3 times power root of FCK. This is the concrete strength. And rho is the tensile reinforcement calculated as AS divided by B times D. If rho less or equal than rho O, we use 7.16A formula. If rho more than rho O, we use 7.16B formula. For this formula, we also required rho prime. So rho prime is the required compression reinforcement ratio, calculated as AS prime divided by B times D. For the value of K, it depends on the structural system, which we'll be seeing in the next slide. This is table 7.4N, basic ratio of span effective depth ratio for reinforced member without axial compression, and we use this table basically to get what is K, so we will be able to use the formula for L over D. Okay, so the K is a structural system. Okay, so this is the structural system and this is the value of K. For simply supported beam, okay, or one or two way of simply supported slab, we use the value of 1. Our K is 1. For end span of continuous beam, we use 1.3. For interior span of beam, we use 1.5. For cantilever beam, we use 0.4. The basic ratio are modified in particular case as follow. For flange section, where the ratio of the flange width to the web width exceed 3, the value should be multiplied by 0.8. For beam and slab, other than flat slab, exceed 7 meter, we should multiply by 7 divided by span. Where more tension reinforcement is provided, mean AS provided more than AS required, we multiply the value by ratio of AS provided divided by AS required. And this value should not greater than 1.5. Let's see the example how to check deflection for the beam. We have the simply supported beam with 8 meter length, and this is the cross section and detailing for the beam. The strength of the concrete is 25 and steel reinforcement is 500. For tension steel, the AS required is 1220 mm square and AS provided is 1257 mm square. For compression steel, AS required is 356 mm square and AS provided is 402 mm square. First, we have to calculate the percentage of required tension reinforcement. So the formula is AS required divided by B times T. So we get 0.009. For percentage of required compression reinforcement, rho prime, the formula is AS prime required divided by B times T. So we get 0.0027. For reinforcement ratio, rho O, we have to square root the FCK, which is 25, times with 10 to the power of negative 3. We get 0.005. For K structural system for simply supported beam, by referring to table 7.4, it is 1. We compare the value of rho and rho O. Since rho more than rho O, we use equation 7.16b. We key in all the data into this formula. We will get L over D is 17.06. This is not the final L over D. We have to do some modification. First, modification factor for span greater than 7 meter. Our question, the beam is 8 meter. So, we have to modify by 7 divided by span. So, 7 divided by 8 meter. It is 0.88. The second modification is modification factor for steel area provided. So, what we should do is we should divide the AS provided with AS required. And this value should be less than 1.5. We have to multiply the basic L over D with the modification factor. This is basic span over D, which is 17.08 times 0.88 for the span greater than 7 meter and 1.03 for the steel area provided. Therefore, we get the L over D allowed is 15.48. To compare our L over D allowed with our L over D actual. For L over D actual, we have to divide our length, which is 8 meter, divided by D, 654. Therefore, we get 12.23. We compare this with the L over D allowed. So our L over D actual must be less than L over D allowed for the safer deflection. This is the last part we should do in design by providing detailing for the beam. Typical detailing for beam should have number of reinforcement, diameter of reinforcement, length and top-bottom reinforcement. Look at this detailing for simply supported beam. We have view of the beam length and the cut section of the beam. Normally, we take at the middle part. H is stand for high yield steel bar. Okay. Previously, we used Y or R, but we still found that till today. That's actually referred to British standard. For the longitudinal bar, we should have number of bar and bar size for top and bottom reinforcement. This is for link, shear link. Okay. HX 3 to 5, this is for shear link near the support, where 325 is the spacing between link. Then we have the length for the shear link. I also want to emphasize on curtailment. Reinforcements are curtailed and cut off along its length in beam, depending on the bending moment at the section. After we curtail or cut off the beam, we provide the anchorage to the beam, to the steel bar. This is the example for simply supported beam and its bending moment. We use the maximum bending moment for determining our area and number of reinforcement needed for the beam. If you see, as the moment reach the support, the value getting 0. If we want to provide same number of bar while bending moment at this area is reduces, we actually waste our steel bar. In simple word, to offer economical design, the bar is curtailed at the section which it is no longer required to resist flexural or bending moment. This is the simple practice for economical design for simply supported beam. 100% reinforcement is provided at the tension reinforcement at the midspan of beam, and 50% is curtailed at the distance 0.08 L from the center of the support. I give simple example. If our beams requires 4H20, at the middle span, we must provide 4H20. At the end span, we can reduce to 2H20, which 50% of the beam required area. This is the simple economical design for continuous beam. The tension reinforcement at the midspan is 100%. while it is curtailed at the distance 0.1 L from the center of the support and 0.1 L at the intermediate support. L is the effective length. On top of the reinforcement, we provide 20 to 60% area. Over the support, 100% tension reinforcement is required. I give example. For bottom reinforcement, in between support, the beams require 4H20. So, the middle span, we must provide 4H20. And the end span can reduce to 2H20, which is around 30% from the mid-span steel bar. For the top reinforcement, the beam requires 4H12. So in between support, we can provide 2 to 3H12. While over the support, we must provide 4H12.